Welcome back to G Fun Facts Online. Today, we are not just talking about a particle, we are talking about a crisis. A crisis that is currently tearing the world of modern physics into two very different realities. It is a story about a tiny, unstable cousin of the electron called the muon, a giant magnet that took a boat ride around Florida, and a stubborn numerical discrepancy that refuses to die. As we stand here in early 2026, looking at the final results from the Fermilab experiment, we have to ask ourselves, are we finally seeing the footprints of dark matter and ghost-like bosons? Or are we witnessing a breakdown in our ability to calculate the basic laws of the universe? To understand why this matters, we have to shrink down. We need to journey into the heart of the quantum vacuum. We often think of empty space as empty, but in quantum mechanics, the vacuum is a boiling cauldron. It is alive with virtual particles popping in and out of existence. And our protagonist, the muon, is using this vacuum as a dance floor. It is wobbling in a magnetic field, and the rhythm of that wobble is slightly offbeat. That tiny syncopation might just be the key to a new theory of everything. Let's go back to the beginning. The year is 1936. Physicists thought they had the universe figured out. You had protons, neutrons, and electrons. The electron was the lightweight carrier of charge. It made sense. But then, Carl Anderson and Seth Nettermeyer looked into their cloud chamber and saw a track that didn't fit. It looked like an electron, and it acted like an electron, but it was over 200 times heavier. The Nobel laureate Isidor Isaac Rabi famously asked, "Who ordered that?" This intruder was the muon. It is the second generation of matter. It is unstable, living for only about 2.2 microseconds before it decays. That sounds short to us, but in the particle world it is an eternity. Because the muon has charge and spin, it acts like a tiny bar magnet. It has a north pole and a south pole. The strength of this internal magnet is defined by its magnetic moment. And the relationship between that magnetic strength and the particle spin is encapsulated in a number called the g-factor. In 1928, Paul Dirac gave us the equation that combined quantum mechanics with special relativity. The Dirac equation predicted that for a simple particle like an electron or a muon, that g-factor should be exactly 2. If the universe were simple, the story would end there. G would equal 2. But the universe is not simple. In quantum electrodynamics, or QED, a particle is never alone. As a muon travels through space, it is surrounded by a cloud of virtual particles. It interacts with them. These fleeting interactions slightly alter how the muon responds to a magnetic field. So G is not 2, it is 2 plus a little bit extra. That extra bit is what we call the anomalous magnetic moment, or AA mu. This is the G minus 2. It represents the deviation from Dirac's prediction caused entirely by the quantum fluctuations of the vacuum. Measuring this value is essentially measuring the vacuum of the universe itself. If the vacuum only contains the particles we know about in the standard model, we get one specific number. But if the vacuum contains hidden monsters, like dark matter particles or supersymmetric partners, they will bump into the muon and change that value. The muon is the perfect candidate for this probe. The electron is too light to feel these heavy virtual particles strongly. The muon, being 207 times heavier, is about 43,000 times more sensitive to new physics. It is the Goldilocks particle, heavy enough to feel the unknown, but long-lived enough to be stored in a magnet and measured. So how do we measure it? This has been a generational relay race. It started at CERN in the 60s, moved to Brookhaven National Lab in New York in the 90s, and finally landed at Fermilab near Chicago. The Brookhaven experiment in 2001 dropped a bombshell. Their measurement of the muon's wobble was higher than the theory predicted. It was a deviation of between 3 and 4 standard deviations. That is evidence, but not proof. When funding ran out, the physics community was left hanging from a cliff for 2 decades. To settle the score, scientists needed a better experiment. They needed Fermilab's powerful particle beam. But they also needed Brookhaven's incredible superconducting magnet, a 50-foot wide, 700-ton engineering masterpiece. Building a new one would cost too much. So in the summer of 2013, they did something audacious. They put the massive magnet on a barge. They sailed it down the East Coast, around Florida, up the Mississippi River, and drove it on a specialized truck to Illinois. It was a logistical opera. If that ring had twisted by even a few millimeters, the superconducting coils inside would have snapped, and the experiment would have been over. But it arrived safely. This brings us to the Fermilab experiment, known as E989. The goal was to measure the wobble with a precision of 140 parts per billion. Let me explain how this machine works, because it is brilliant. It starts with protons slamming into a target to create pions, which decay into muons. We filter out a beam of antimuons at a very specific speed, known as the magic momentum. This is about 3.1 GeV. Why this specific speed? Because to keep the muons inside the ring, you need to use electric fields to focus them. But electric fields can mess up the magnetic measurement. At exactly this magic momentum, the effect of the electric field on the spin cancels out perfectly. It's a sweet spot in the laws of physics. So these muons enter the storage ring. They circulate in a vacuum chamber surrounded by a perfectly uniform magnetic field. As they circle, their internal spins rotate, or precess, like a spinning top. Because g is not exactly 2, the spin rotates slightly faster than the muon itself circles the ring. The spin axis drifts. When the muon dies, it shoots out a positron. The direction of that positron tells us which way the muon's spin was pointing at the moment of death. We have detectors lining the ring to catch these positrons. When you plot the arrival of these positrons over time, you don't get a flat line, you get a wave. It goes up and down as the spin rotates past the detectors. This is the famous wiggle plot. The frequency of that wiggle tells us the value of g-2 directly. But there is a catch. Human beings are biased. If you know the answer you are looking for, you might subconsciously tweak your analysis until you find it. To prevent this, the Fermilab team used a blinded clock. The master clock of the experiment was set to a secret frequency known only to 2 people outside the collaboration. For years, the physicists analyzed the data in blinded units. They had no idea what the real number was until the very end, at the unblinding ceremony. In 2021, they released the first result. It matched the old Brookhaven number. The anomaly was real. The tension with the standard model rose to 4.2 sigma. Then, in June 2025, came the final release. The full dataset runs 1 through 6. The precision hit 127 parts per billion. The experimental number is rock solid. If you compare this 2025 result to the theoretical prediction from 2020, the discrepancy is over 5 sigma. That is the gold standard for discovery. In any normal timeline, we would be popping champagne and accepting Nobel Prizes for discovering new physics. But this is not a normal timeline. While the experimentalists were perfecting their machine, the theorists were having a civil war. This is the plot twist that nobody saw coming. To claim we found new physics, we need to know exactly what the old physics predicts. The standard model prediction is a mix of electromagnetism, the weak force, and the strong force. The electromagnetism and weak force parts are easy. We know them to incredible precision. The problem is the strong force, specifically the hadronic contribution. Quarks and gluons are messy. Historically, physicists couldn't calculate this from scratch because the equations are too hard. Instead, they used a data-driven approach. They looked at other experiments where electrons and positrons annihilate into hadrons. They used that data to calculate the muon's interaction. This is called the R-ratio method. All the old data agreed, and it predicted a value that clashed with the muon experiment, hence the 5 sigma anomaly. But recently, a new challenger appeared. Lattice, QCD. This involves simulating the strong force on a supercomputer by chopping up space-time into a grid. For years, it wasn't precise enough. But in 2021, the BMW collaboration published a result that shocked everyone. Their supercomputer calculation claimed the hadronic contribution was actually higher. If you plug the BMW number into the standard model, the prediction for g-2 moves up. It moves up right on top of the Fermilab experimental result. If the lattice calculation is correct, there is no anomaly. The standard model is fine, it was just a calculation error in the messy hadronic soup. To make matters even more confusing, in 2023, a new experiment in Russia called CMD3 measured the electron-positron cross-section again. And unlike all the previous experiments, their data was higher. It pointed in the same direction as the lattice result. So, by 2026, we are in theoretical purgatory. We have an incredibly precise measurement of the muon from Fermilab. But we don't know what to compare it to. If you trust the old data, we have discovered new physics. If you trust the new lattice calculations or the CMD3 data, we haven't. Physicists are trying to find a middle ground using something called window observables. This looks at specific energy ranges where both methods should agree. The results there strongly favor the lattice calculation, suggesting the old data might have had systematic errors. So the consensus is slowly shifting. The anomaly might be disappearing into the noise of the strong force. But what if it is new physics? Let's dream for a moment. If the discrepancy is real, what could it be? The most famous candidate is supersymmetry, or SUSY. This theory says every particle has a heavy superpartner. A muon and a neutralino could be circulating in that vacuum loop, pushing the g-factor. But the Large Hadron Collider has been hunting for SUSY for 15 years and found nothing. Another option is the dark photon. This would be a force carrier for a hidden dark sector of the universe, interacting slightly with our world. It could explain both the muon anomaly and dark matter in one go. There are also leptoquarks, hypothetical bridges between leptons and quarks. Or perhaps a second Higgs boson. The possibilities are tantalizing. But science doesn't stop at a stalemate. Even as theorists argue, experimentalists are building the next check. In Japan, at the J-Park facility, a new experiment is under construction. They are taking a completely different approach. Instead of the magic momentum and a huge ring, they are using ultra-cold muons. They cool the muons down until they are almost stopped, then accelerate them into a much smaller magnet, only about 66 centimeters wide. This removes different types of systematic errors. If J-Park agrees with Fermilab, the experimental number will be indisputable. If they disagree, well, then we really have a problem. J-Park is expected to start taking data around 2027. Beyond that, the technology developed for these experiments is paving the way for a muon collider. Smashing muons could allow us to reach higher energies than ever before, potentially finding the particles that the LHC missed. So what is the legacy of the wobble? As we view the landscape in 2026, the Muon g-2 anomaly remains the most tantalizing maybe in physics. The Fermilab experiment has performed a masterpiece of measurement. 127 parts per billion is an achievement that will stand for decades. Whether this result breaks the standard model or just forces us to understand the strong force better, the outcome is profound. If it is new physics, we have opened a door to the dark sector. If it is the standard model, we have mastered the quantum universe to an unprecedented level. The muon, that heavy, unwanted cousin, has proven to be the most faithful guide we have. It wobbles in the dark, and by measuring that wobble, we are slowly, painfully, but surely, mapping the invisible fabric of our reality.